So, welcome again to the lecture course on Relativity and Cosmology. We are now entering the part 2 now in the summer term. And in my last lecture of the winter, I gave you already an overview of what we do, so I do not repeat it here. What we do first is to discuss in some detail experimental and observational tests of Einstein's theory. Most of it will deal with the Schwarzschild metric that we derived at the end of the winter in chapter 8. And there you see the full power of Einstein's theory. You really see that this is a physical theory that gives you effects even in everyday life. So what we do actually is we take the Schwarzschild metric that we had derived in chapter 8, and let me write down the Schwarzschild metric for you, which is ds squared, and I include the speed of light explicitly 1 minus 2 gm over r c squared dt squared. So that's the temporal part, and then we have the spatial part, which is the inverse of that, so 1 minus 2 gm over r c squared to the minus 1 dr squared plus r squared d omega squared. And this here is dimensionless, and it's the ratio of the Schwarzschild radius 2 gm over c squared over r. So except for one effect that I will discuss at the end of chapter 9, the so-called Thirring-Lense effect, all the tests are based on this metric. For the Thirring-Lense effect, we have to include as a perturbation some rotation. Now, classic tests or historic tests, usually when we talk about classic tests, we mean three things. The first is the gravitational redshift, which is equivalent to the gravitational time dilation, and we already discussed this in section 4.2 on the basis of the equivalence principle. And as I will show you, based on the full treatment, we get the same result. So there's no modification here. Then the next test is the light deflection near the sun. Of course, today we observed this at many other occasions, but originally it was near the sun. I mean that you have a big mass like the sun, and you have a light ray that is attracted. And so light deflection near the sun, I should say, if I talk about the classic test. And the third is the perihelion motion. Perihelion motion of, historically of the planet Mercury, which is the innermost planet in the solar system, and the planet that is closest to the sun, and this is why the effect there is biggest, in spite of Mercury being not so easily visible. You could also add some derived effects, such like the geodetic precession or the Shapiro effect, which I will also include. And we will also add one effect that was predicted very early, but measured only this century, and this is the already mentioned Thirring-Lense effect, which goes beyond that form. So that's the plan for the chapter 9, and the first section is devoted to the gravitational redshift. So let me do that first. So 9.1 is the gravitational redshift. So let me briefly recapitulate what we had in section 4.2. There we had this picture of that rocket that accelerates through interstellar space with acceleration g, and we have here an apparatus. So we have here A and B, and we send a photon here from A to B, and we have here the height h. And we have argued from the equivalence principle that oh, first I should say from directly from the acceleration, we know that there is a redshift coming from the Doppler effect, but the equivalence principle then tells us that the same effect should be present when the rocket is at rest on Earth, where the gravitational acceleration is g. So, and this is then the gravitational redshift z, which is defined as always the change of the wavelengths over the wavelengths, and we have found that this is g h over c squared, where g is the absolute value of the gravitational acceleration and h is the height. And if we add the gravitational potential phi, the Newtonian potential, then we have a delta phi. I mean, this is a very small distance, so this is just g times h, and so we have delta phi over c squared. So that's a result that we derived for the rocket, and we concluded from the equivalence principle that is also be true for static gravitational field. That's a gravitational redshift. I mean, of course, it can also be a blue shift, but the terminology calls it redshift. As a consequence, clocks are also slowed down in a gravitational field. So I should emphasize this again. So consequence, clocks are slowed down in a gravitational field. And we call this the gravitational time dilation. Now, you know from special relativity the velocity caused the time dilation. Now this is an effect already in a static field, and it's called the gravitational time dilation. So why is that? Well, I mean, consider, say, a situation on Earth with here gravitational acceleration g, and we have, say, a lower observer and a higher observer A and B, and if we send here, say, a light, I mean, which is a wave from A to B, and consider a constant number of waves, so maybe 10 waves come from here to here, then the number of waves can be written, of course, as the product of the frequency and the time interval. No? So number of waves is the frequency times time interval. So the frequency we have seen here in B is smaller than in A. That's the gravitational redshift. But if we have the same, I mean, a constant number of waves, I mean, 10 emitted and 10 received, say, for example, then of course this time interval in B must be greater than in B, which means that the clock in B runs faster. So this is smaller in B, so delta t must be greater in B than in A. Now, so the clocks are, as we say, slowed down if we are closer to the center of a gravitational field. Now, how would we treat this generally? So generally, which is a non-static situation, it looks as follows. So I first explain the situation, and then I, for illustration, recover from this the static effect, and then give you the formula for the general effect. No? So instead of saying here have a static observer A and a static observer B, we consider two dynamic observers. I mean, one we call the source. This is where the light is emitted, and the other we call the observer. No? So we have two world lines, one of a source S and one we call observer O. So these are world lines, and let us consider the emission of photons here from the source and here the first one, and the classical electromagnetic wave, and here a second one. No? So this I call here with gamma, and I call here the proper time that elapses ds0, and this I call here ds1. And so these are the events I call S0 and S0 prime, and these are the events O1 and O1 prime. So what I mean is these are the same number of waves. I mean the same number of waves here, maybe 10 wave crests are emitted, and here those 10 wave crests are received. Now let us call the emission frequency here nu naught. So this is the emission frequency of the light, and this here nu 1 is the detection frequency of the light. Measured in the respective rest systems of source and observer. And of course we define, I mean the frequency is 1 over the period, so nu1 over nu naught, I mean is this identical to ds0 over ds1. No? So we have here in the respective rest systems the corresponding proper time, of generally the proper time, and this is inversely proportional to the frequency. No? So that's how we define, and this is what we take as the definition. Now let us first go to the static system and see how we can derive this heuristic formula from earlier, and then we go back to the general situation. So A, we have then the static gravitational field. So we have here the Earth, say, and so we have here at distance r0 the source S, and we have here at distance r1 the observer, well, coordinate distance I should say, and of course we emit here a photon from here to here. So the metric here is the static metric of Schwarzschild, so G mu nu only depends on R. No? So that's here what we have here. And so the S squared is G mu nu dx nu, which is then G00 dt squared plus GAB dxa dxb. Now it's a general form of the static metric, so we will insert the particular values here later. Yeah. So let us proceed here. So if we consider the source, which is here at rest, then we have ds0. We only have the first term from the G00, and so we have square root of G00 S0 dt 0, and we have for the observer also at rest. So this is here observer and source ds1, which is square root of G00 at the position O1 dt1. So in a static situation only the G0 terms remain, and then if we consider now a light ray from the source to observer just in radial direction, so we can immediately calculate the time. So if you have a radial light rays, we have the squared, the S squared is 0, no? That's the null geodesic, and so this is G00 dt squared plus g r dr squared. Okay, the g00 is negative, so we can write as minus the absolute value of g00. So that is, you get from this immediately the coordinate time difference, so t1 minus t0. So this is the coordinate time from source to observer, and this is then the integral from r0 to r1 square root of g r over g00 dr. And because this is time independent, I mean, if you do it also for at a later time again, then of course you get the same result. No? So okay, I could call it t1 prime minus t0 prime, so this is t independent. No? So from this then I get that t0 is equal to dt1, as you would immediately expect from the staticity. And having our formula here then gives that v1 over v0, which is ds0 over ds1. It's just the ratio then of the square roots of the g00. So we have just here the square root of g00 of s0 over g00 at 01. So if you have this terminology, so you see for a static gravitational field, the gravitational red or blue shift is just given here by the g00 component of the metric. And let us now introduce here the expression from the Schwarzschild metric, which is here. No? So this is here the g00. And let me now again take into account the speed of light, so that we see in the result that we get back the old ones. So if we have g00, which is minus 1 plus 2 gm over rc squared. We have here the Newtonian gravitational potential, gm over r. So that's minus 1 plus 2 phi over c squared. And we have to insert this here. I mean, to get back the old result, of course, we have to take this here as a small quantity so that we can make an expansion. So we have v1 over v0, which is then 1 plus 2 phi naught over c squared divided by 1 plus 2 phi 1 over c squared to the 1/2. And so we can, I mean, use 1 over 1 plus x is approximately 1 minus x. So let us do this here. So this is 1 plus 2 phi naught over c squared times 1 minus 2 phi 1 over c squared to the 1/2. And okay, out of these 4 terms that you get, of course, the last one, this times this, is also negligible because it's a small quantity squared. So then this is roughly 1 plus 2 phi naught minus phi 1 c squared to the 1/2, which finally, I mean, from expanding the square root is approximately 1 plus phi naught minus phi 1 over c squared. Now, and you see this is just our old result that we got in the section 4.2 from the equivalence principle. No? So this was our delta phi. And so we get that if you want to have really the same formula, then you get from here that nu1 minus nu0 over nu0 is approximately delta phi over c squared. No? So then the 1 is gone in that expression. So you see here that's our old result, no? Which is for a small height in this Newtonian limit, but using the equivalence principle. This is what we had guessed, and you see the exact calculation justifies this result. I mean, this here is the exact solution of Einstein's equations outside a spherically symmetric mass. So if we apply this and we make the corresponding approximations, we get back the old result. But you see that, of course, this is much more general. No? So for general static metric, I mean, we have here this result here, and so you can, even if this is not small, just use here the G00 from above, and you get correct and exact result. No? For example, if you have a satellite high above, of course you have to consider its motion, but apart from that, I mean, for the radial direction, you can just use this here. No? So when you send light signals between satellites, then I mean, most of it, if you neglect the velocity, comes from that. But of course, in general, the velocity is not negligible, and so we have to go back to this general result. So let us do this now. So let us now come back to the general situation. So so this is then part B here, general situation. And let us consider again here the two world lines, but I write this down again to introduce some more notation. So we have the world lines of source as not an observer, O1, and let us consider here now the emission of the photon. So I indicate here a curved line because it's in general curved space-time. So we have here then the 4 velocity tangential, which is U0 mu, and here also the 4 velocity U mu1, and let us call the wave vector, the wave 4 vector of the light ray here k mu. No? So that's a null vector. And they are in an arbitrary gravitational field, and they are in arbitrary motion. So no special case here. Now let us write down again the line element ds squared, which is g mu nu dx mu dx nu. And if we divide by one of the two sds in ds squared, we can write this as ds is g mu nu dx mu times dx nu over ds, and this is of course the 4 velocity by definition, and so we have here g mu nu dx mu u nu. No? So that is just what we, by rewriting the expression, find. So having this definition, nu1 over nu0 is ds0 over ds1. No? So ratio of frequency inversely given by the ratio of proper times. So then we have here that nu1 over nu0, which is ds0 over ds1, is then from this expression g mu nu u mu dx nu not over g, well, this refers to the source, and g mu nu u mu dx nu 1 and to the observer. No, so that's the general result. I mean, we cannot, in the most general case, I mean, specify this further. So this is then the frequency shift through the relative motion of a source and observer as given by the respective four velocities, and so this is this here, and the metric. No? So you see both the effect from the metric, which is the, you might call the gravitational redshift, and this effect from the velocity, which you might call the velocity redshift, as we know from special relativity. No? So here we have then the frequency shift through relative motion, which is from the respective four velocities, and gravity, which comes from the metric tensor evaluated at the two world lines. Now, in general, we cannot separate the two contributions. No? In general, you just have one effect. Only in particular situation can we say, well, this is a velocity redshift, or this is a purely gravitational redshift. No? Like in the static situation here, which I calculated before, there is no motion, no relative motion, and so only this part, which comes from the G0 components, contributes. You could also, for example, just set here the Minkowski metric, and there is relative motion, and you will get then the old time dilation from special relativity. Now, all of this is included in this general formula. Case 1, of course, if I had not already calculated it, case 1 can be generally recovered if the metric is diagonal and if observer and source are at rest in this coordinate system. So let me just mention this briefly again. So case A is recovered if the metric is diagonal. No, that's important. And if source and observer are at rest in this coordinate system. And a coordinate system which the metric is diagonal. So, and then of course we have u mu is in this coordinate system u 0 and 0, 0, 0. Now the u0, how can you write it? I mean, you must remember that the four velocities are normalized to 1 or to -1. So we have g mu nu, mu is -1, and of course this is then in that situation, and if the metric is diagonal, g0, 0, u0 squared, and so from this you get that u0 is 1 over the square root of absolute value of g0, 0. And then it's clear from that formula that you will find back our old expression. So nu1 over nu0 is then in this case g0, 0, 0 dx0 naught over g0, 0 u0 dx0 at a point at the world line 1. So this is square root of g0, 0, 0 over g c0 1 times dt naught over dt1, but in the static situation we have seen, I mean, this is 1, so we have then just the expression g0, 0, 0 over g0, 0, 1, which is our old expression, no? that we got No? So you could have I could have immediately started from that picture and with that definition given you this general formula from which all cases, all particular cases that you know and you will become to know follow. So that's what you should have in mind. I mean, keep in mind, I mean, the definition of the frequency via the proper times, and then to rewrite this in that form where both the relative velocities and the metric enter. Now, having calculated the gravitational redshift effect and justified it from the underlying exact solution of Einstein equations, we of course ask the question whether we can observe this effect in experiments or in observations. So let me say something about the experimental tests, and this is of course very important for physical theory. Experimental tests. So of course terrestrial experiments, say in a lab, are at a level where the gravitational field can be assumed to be static, and where we can assume to have this limit that we already, of the formula that we already had from the equivalence principle. No? So, which would mean having d nu over d nu is delta phi over c squared. The first tests, of course, they are at the level of this formula. And for this test, it's helpful to parameterize possible violations by a parameter, so that we write delta nu over d nu is 1 plus, and in the literature it's mostly called alpha, a dimensionless parameter, times delta phi over c squared. No? So the correct value from the theoretical point of view is alpha equal to 0, but of course we never know. We want to check our theories. Now, observations have been made over many decades in astrophysics with white dwarfs. You will encounter them later in the course. I mean, compact objects where you have then a redshift coming from the Doppler shift of the spectral lines that you observe. But those observations were too crude to really can be called a test of that effect. Now, there are too many uncertainties concerned with those spectral lines, also with the separation of the gravity effect and the velocity effect. So the first, I mean, real experiment was the one end of the 1950s. So these historic experiments, and they were done by a group at Harvard, by Pound, Repka, and Snyder. So it started in 1959, and there were several improvements in the following years to the mid-60s, and so they had a tower in Harvard which had in that case a height of 22.5 meters. No, so from this, I mean, using this formula, you would get the GH over c squared. No, that's GH here of around 2.5 times 10 to the minus 15. No? So that would be really the relative change in frequency. And you see, this is certainly was challenging at that time. So how could you measure such a small effect? And this was possible at that time only because short before they started, I mean, a new effect was discovered in nuclear physics, and this is the so-called Mössbauer effect. And without this Mössbauer effect, you would not be able, or at least at that time, to measure this. So what okay, for a concrete situation we have the source and the detector, and so we have here our photon that we sent here, and what they used was iron, 57 iron here, I mean both for the source and detector. So the point is, okay, you have a certain you have spectral lines, of course, and you emit these photons, and you have here emission and here absorption. So the point is that you can measure such a small effect only if the frequency uncertainty is very small. I mean, if you have typically spectral lines which are very broad, then I mean this effect would be drowned. But the Mössbauer effect, which was discovered in this or some of these years earlier, they circumvented that. No? So if you use atom crystals, so that you have recoil-free emission, and I don't repeat here that material from your elementary classes in experimental physics. So this, for us, it's important that this effect gives us very sharp spectral lines. So here, this here emits gamma rays with small frequency uncertainty due to the Mössbauer effect, named after German experimentalist who discovered this actually in his very young years, and he got for this the Nobel Prize already in 1961. And I should say that in particular these experiments here of Pound, Repka and Snyder were mentioned by the Nobel Committee as one of the many justifications. I mean, the discovery of this effect is important. First, the effect is of course interesting in its own right, but of course, as you can see already here, it has many applications, and these applications go much beyond these gravitational applications. Now you have a sharp line, and so you emit this, and you want to absorb it here, but this only worked if, of course, here the frequency would be the same for the absorption. But as I just as we discussed, we have here gravitational redshift, so the photon comes here redshifted and does no longer fit to be here absorbed. So what do you do? Well, you just move here this detector a little bit down, and then you get a blue shift effect from the standard Doppler shift. And so you just you just move it in such a way, I mean in your experiment, such that you have absorption. And then by the velocity that you needed to move this detector, you could calculate then the frequency shift. That was a very clever idea, and that worked surprisingly well. So absorption reached by moving the detector downwards to compensate the gravitational redshift. And this leads to a measurement of that redshift, of the redshift. Also, of course, you then change the role of source and detector to reduce errors. So you send the photon from the ceiling to the floor, and you move then this upwards, and then you can give a measurement. Now, then this was confirmed to an accuracy from %. No? So with the accuracy 10 to the -2, this formula here was confirmed with the value then alpha to 0. Now, a more precise experiment was done around 15 years later, actually by a rocket. And this is also historically important, so a more precise experiment by a mission that is called Gravity Probe A. So Gravity Probe B will play an important role later in that chapter, but this was Gravity Probe B, and they had a hydrogen maser in a rocket that was flying in some height, and this was in 1976. And I don't give the details of that, but they could find a limit on this potentially violating term, that this is smaller than about 2 times 10 to the minus 4. Now such measurements continue. I mean, the effect is not, compared to other effects that we will encounter, is not known that precise, but there have been some advances over this. Let me mention two. I mean, there's a whole literature, but let me mention just two. One is with the so-called Galileo satellites. I will in a minute mention these navigation and positioning systems. So that's the European equivalent to the GPS. And the point was somewhat funny, because two of them that were launched, I mean, various years ago, they were unintentionally put into eccentric orbits. I mean, this was not the original plan, so they were not so useful, these early ones, for their purpose, but they were useful for relativists to test this effect. And so they could then improve, I mean, using just data from these. I mean, they were anyway there, so there was no need to construct something for measuring this effect. They could just use the data and could improve this by a factor of 4. So, I mean, you might wish to read the literature. So this is in Physical Review Letters in this volume. And this year, so it was published in 2018 using data of from a couple of years earlier. No, so factor of 4 improvement. No, so this was then, of course, a rather cheap experiment, because you could use data. And a more recent measurement in the lab by the University of Tokyo, which was published in 2020, they give actually for this alpha a value of 1.4 plus minus 9.1 times 10 to the minus 5. No? So do you see at that level here, it's certainly consistent with 0. Okay, this is one side of the coin. We have seen that gravitational redshift is equivalent to gravitational time dilation. No? So when you measure gravitational time dilation, you also measure this effect. And actually in the 1970s, it was again planned to do this with clocks and satellites. Relatively expensive experiments, but before that, two clever scientists in the US found out that clocks were at that time already so accurate that you could measure it in ordinary airplanes, which is much cheaper than constructing a satellite. And so this was the famous Haefling and Keating experiment that you find in all textbooks on relativity. And we plan also to do an exercise on these issues in 1972. So test of gravitational time dilation by using atomic clocks in airplanes. So they just hired such an airplane, and they put these clocks, these atomic clocks in, and then they flew around the Earth in two directions, so to reduce the measurement errors. And the effect, well, in that experiment would be of the gravitational time dilation about 300 nanoseconds. Okay, this is small, but it was measurable already at that time. And they found it with an accuracy, well, not too overwhelming, but 10%. So, I mean, for such a pioneering experiment, that's good. Nowadays, of course, experiments are much more precise. So concerning, say, this effect that comes from just having a height, now frequency shifts are already observable. I mean, for that size of the height in the laboratory, and it's planned to go down to a couple of millimeters. No? Already that you can observe the redshift by having sending a photon only over a couple of millimeters. I mean, that's really impressive, and it's made possible by technological advances in quantum optics. That is a field in its own, and it's very interesting. Now let me end this brief overview of the experiments by emphasizing the relevance for the everyday life. Okay, I mentioned already here in that context the Galilei satellites. I mean, they are built in analog to the GPS, the global positioning system, that is already around with us for a couple of years, and which is used to measure precisely the position on Earth, actually to maybe 1 meter. So let me mention this GPS. So if you want to have a precision of 1 meter and below, of course, 1 meter certainly for some purposes. What kind of time, if this operates with light signals, I mean, what precision you need for the time uncertainty? Well, this you can estimate if you have t as 1 meter over the speed of light, which is about 3 nanoseconds. That would be the time uncertainty that corresponds to this, say, 1 meter space uncertainty when using light rays. And the GPS, how does it work? I mean, you find a lot of literature on this. For us, the details are not relevant. We have 24 satellites which are flying around 20,000 kilometers height, I mean, above the Earth, such that at least 4 satellites are visible from every point on the Earth. So they are spread around, and you should see at least 4, and they send electromagnetic they contain, of course, atomic clocks, very precise one, the best ones what we have, and they send electromagnetic signals and send information about the time of emission and the position of emission. And of course, the constancy of the speed of light is very important in this. So an observer on Earth, I mean, can receive the signals and determine the position from this information. I mean, he needs 4 coordinates. I mean, 3 for the space. I mean, the 2 for the on the floor and 1 on the height above the Earth, and also the time. So 4 coordinates are needed, and this is why you need at least 4 satellites to be visible. And of course, you can calculate, or the computer of the GPS calculates from that information, from the arriving light signals and the information about the position of the satellites and the time of emission, then the position on Earth and the time. And because of this because of this precision here that you need definitely the effects of both special and general relativity. So effects of special relativity, this is from moving satellites, and And general relativity, that's from the gravitational redshift, they are roughly, 50,000 nanoseconds per day, for these satellites. So you see 50,000 nanoseconds per day. If you somehow would deny relativity and work with Newtonian theory, then you would have, of course, within one day, a totally mismatch of the factual position and what you get from your instrument. So this would lead within one day to an error bigger than 10 kilometers. And you could not use that, certainly. If you want to come here for the lecture and you use a Newtonian instrument, then you come back, you go to Düsseldorf or whatever. So that's certainly not possible. Few people, of course, few users are aware of that, and they don't need to be aware of that. But for us, it's really a success story that, relativity, which started 100 years ago, more than 100 years ago, as a fundamental theory of gravity, has reached, everyday applications. You see that this started in end of 50s, with the first real experiments. So just 40 years or less until the GPS was constructed. So very short, relatively short time from fundamental experiments to applications. So far for 9.1 and for the gravitational redshift. So the section 9.2 will be a longer section, and we will spend really some time and some care to discuss other effects, in particular the light deflection near the sun and the perihelion motion of Mercury. These are really fundamental experiments, and every course on relativity, of course, will discuss them in great detail. They were also important for accepting the theory historically in its very early time, and for making Einstein famous, as you will see. So we will, for this purpose, study null geodesics and also time-like geodesics in the Schwarzschild metric. So the situation will be to have, say, the sun, the massive sun in the center, and we have the motion of the planets. This we need for the perihelion motion, and these are on time-like geodesics. And we have the dynamics of light rays, for which we need a null geodesic. So what we first will do, we derive the orbital motion of those geodesics in the Schwarzschild metric, and from this we get the effects, the predictions, and I tell you about really how precisely known they are. So thank you for today, and until next time.